So, an IP address consists of two main portions. We have the network address portion, also known as the network ID. This identifies a specific network. Routers maintain routing tables that contain network addresses. It's important to realize that routers build their routing tables based on the network address and not on the host address. So they do not route packets from one interface to another interface based on IP addresses. They do their routing based on network addresses. So they will look at the destination IP address in a packet and match that to a network address in their routing table to determine how traffic is routed. So an IP address consists of the network portion as well as the host portion, which is also called the host ID. This identifies a specific endpoint on a network, such as a server, a printer, a PC, an iPhone, an iPad, or some other type of device, including IP phones. These are essentially the devices that need to communicate with each other. So a PC may be communicating with a server. You may be using your iPad to read the news. So you'd be surfing to CNN.com or USAtoday.com or the BBC. So your iPad is sending traffic to that server, and the server is returning traffic to your iPad. So the iPad and the server will have a TCP session established at layer 4, but for the iPad to communicate with the server, routers need to route traffic to the server and back again. So here's an analogy to explain network and host. In cities throughout the world, you have streets. So, as an example, we have Oxford Street. On the street, we have multiple houses or multiple offices. But in my example, let's assume we have houses on the street. Each house has an individual house number. So we have, in this example, 1 Oxford Street, 2 Oxford Street, 3 Oxford Street, 4 Oxford Street, 5 Oxford Street, and so forth and so on. Each house number uniquely identifies that specific house on this street. Now, you wouldn't have 2 houses with the same number on the same street. That would be very confusing, because perhaps you want to meet your friends, the Joneses, at number 1 Oxford Street. But you may end up spending your day with a totally different group of people if you have 2 houses with the same number. In this example, we have 2 number 1 Oxford Street houses. Which house is the correct house? Now, that's not desirable. When you go to 1 Oxford Street, you want to make sure that you're going to the right house to meet your friends rather than going to some other house. And hence, house numbers need to be unique on a street, in a city, in the world. Now, continuing with our analogy, when working out how to get to a remote destination in the physical world, let's say you want to go to Oxford Street in London in the UK, and you've never been there before. You may use a mapping technology such as Google Maps to find out how to get to that specific street. Now, when you're doing this, you don't look at individual house numbers, but rather look at street names to determine your way to get to that destination. So if you're in a different part of London, you may use the street name to work out how to get from your current street to Oxford Street. And when you get to the destination street, then you're able to look at house numbers to determine which house number to go to. Technologies such as Google Maps are obviously really intelligent and know the house numbers and will guide you to the right part of the street. But for this analogy, think of how routers route. They will route traffic to a destination network, and when traffic gets to that destination network, then house numbers are used or IP addresses are used to determine which host to forward the traffic to. Now, in a similar way, the network address, in this case 10.1.1.0, identifies a specific network somewhere in the world. Host addresses such as 1, in this example, identify individual devices on that network. So 1 identifies this PC on network 10.1.1.0. Each device on this network has a unique number. So in this example, we have 5 unique devices, in the same way that in our previous analogy, we had 5 houses on Oxford Street. Now, in the same way, you wouldn't configure multiple PCs or multiple devices with the same IP address as that would cause confusion and conflicts. So as an example, if another device wants to communicate with 10.1.1.1, which PC would it send the traffic to? If PC5 wants to communicate with this host, 10.1.1.1, there are two hosts with the same IP address. Which device should PC5 communicate with? So, devices on a network or subnet, which we'll talk more about in a moment, have a unique IP address in the same way that a house has a unique house number on a specific street. So in the same way that we use street names when going from A to B, routers look at network addresses to determine how to get to a remote destination. Other protocols such as Address Resolution Protocol or ARP are used to find the house number or host number for a host on a specific street or network. So in this analogy, we're going from Queen Anne Street to Oxford Street, and we would use street names for our directions as per this example. But once we get to the street, in this case Oxford Street, we would look for the specific house by looking at house numbers in the physical world, or in the network world, we would use a protocol such as ARP to find the specific host on that network. Routers do not make routing decisions based on IP addresses, they make it based on network addresses. A router's routing table is not populated with IP addresses, it's populated with network addresses. The destination IP address in a packet is then matched to the routing table, populated with network addresses, and then a determination is made to decide out of which port or interface on the router the packet should be forwarded.